What's up, everyone? Buckle up for a new episode of Tech in Check. Let's dive into the basics and complexities of machinery maintenance with engineers Rich Marriage and Tony Planamento. Join us as we meet with guests from the marine and industrial world to learn about the latest technology that keeps your equipment in check and working for you.
For Advanced Mechanical Enterprises, I've been in business I started in 1992, and been in business over 30-something years. And Tony is...
I'm Tony Planamento. I'm the technical project supervisor here. It'll be 8 years in May.
We specialize in vibration analysis and laser alignment of rotating machinery. We've gotten involved in...
The next slide. There you go.
Okay, so 4 segments of our business. We do testing and analysis using vibration analysis, ultrasound. We do torsional vibration analysis. We do alignment. We use borescope alignment. We do laser alignment. We have laser scanning technology for 3D scanning.
Laser tracking.
And we have a laser tracker for doing precision geometric measurements. So we have some pretty sophisticated tools for alignment. And then we have, as you can see, we do welding and machining and fabrication work as well. That's our machinery services. We overhaul pumps and motors and things like that. And then we also represent several products. Tony is leading that up. We're working closely with a company called Fluke. They make laser alignment equipment. They have a division called Fluke Reliability Services, where and that's whose equipment we are currently utilizing for vibration analysis and condition monitoring of machinery. And also a lot of our rotating machinery lasers come from Fluke. Anything you want to add?
No, I think you got it.
All
right. So the main topic of the presentation today is going to be motion amplification. There are a few different manufacturers. We predominantly use RDI. They actually invented the technology. It's a very interesting story. The CEO actually had his PhD in astrophysics, and he created this software to try and detect flickering of starlight. And at one point, while he was testing this software, he accidentally pointed it at his sprinkler pump. And the whole thing was just oscillating like crazy. And he was like, oh man, that's a really cool application. So that's when he developed that company and that technology to go more into that rotating equipment aspect of things. So I don't know if you guys noticed the tagline of the presentation is seeing is believing. That's kind of their tagline as well. So if a picture's worth 1,000 words, what's a video worth, right? So the basics of this software is essentially you have a high-speed camera, and the software, it's a specialized software. It does post-processing of the video, and it's actually looking at the deviation in light intensity across each pixel of the camera. So as it plots that deviation in light intensity and it converts it into a displacement waveform. And then the software can actually do all of your FFTs to get it from, the time domain into the frequency domain, enter vibration analysis.
Yeah, so every pixel is a vibration measurement point.
Yeah.
So it's very powerful.
Yeah, it's incredibly powerful.
And we have found that, I have found in being in this business for years, try to explain frequency plots and waveform plots to a yacht customer or anybody who's an operator or maintenance guy, and they look at you like you got 3 heads. So with this technology, we'll video a machine, and then through post-processing we can generate a video that they can actually see what is going on and what defect they may have in their equipment. It's some pretty exciting stuff, because it's just such a pleasure to be able to show people this video, and it just you know, they just, all the questions just kind of like melt away.
If you want to hit the next slide. So kind of what Rich was going into, these are kind of the bullet points of how this technology is at least helping us, but very, very many people in the industrial sector are actually using this as well. So you can see all the different types of pipe movement. So basically, you know, you've got intuitive understanding. Like Rich said, you can show video instead of showing plots and trying to explain your plots, right? Because then people are more relying on your word and your expertise, which obviously is a very key factor, and it's, you know, it's humbling, right? Because you're relying on somebody else to trust you. But when you have this video, it really takes away that leap of faith aspect, so to speak. You know what I mean? Visual confirmation, again, picture's worth 1,000 words. What's a video worth? Enhanced communication, very, very quick. So if you look down here, this is the still video. This is what the human eye is seeing, right? So it just looks like a carbon fiber shaft running true. This is after it's been processed through the software. So you can actually see it's kind of whirling.
It's a drive shaft on a high-speed ferry. Carbon fiber drive shaft.
So instead of a half-hour conversation trying to explain to the guy, hey, you know, this is oscillating at first order vibration, you know, it's an eccentricity, or it's bending due to dynamic misalignment, something along those lines. You can just say, hey, look at that video. This thing's moving. We gotta fix it, right? So it brings that immediate insight aspect to things.
And now, obviously, this is controlled. The post-processing has a feature, you know, where you can control the amplification.
Yes. So there's many features to the software. The most powerful part of things is, like Rich was saying, every pixel is a different vibration sensor. But you can also then go into that video and filter to specific frequencies. So I don't know how much everybody knows about vibration, but generally you're looking at multiple frequencies combined together. And when you get it into the frequency domain through the fast Fourier transform, it starts to isolate those peaks, right? This, you can actually, it does the same thing where the video shows every frequency at once. But then you can draw a square, they call it an ROI, a region of interest, and you can filter that particular point of interest, region of interest, to whatever specific frequency you're looking for. First order, second order, blade pass frequency, so on and so forth.
So this is filtered to first order.
Yes.
Which is shaft rotation. It's a fundamental, we call fundamental frequency vibration.
Yeah. Yeah, there you go. That's just the Delaware. Okay. Delaware dredge.
All right, so this is a fairly recent job we just did for a dredge that was less than a year old. They have a 5,000 horsepower pump that they use for dredging, for moving the dredge material. And the coupling between the gearbox and the dredge pump itself. So you have an engine, and let me see here. You know, it doesn't show the arrangement, but you have a main engine. You know, you have a dredge engine, then you have a gearbox, and then you have you have a clutch assembly, gearbox, and then you have a dredge pump. Coupling. And the coupling between the dredge pump and the gearbox was failing. So the guys ended up, the dredge was offshore off the coast of North Carolina. Took a small launch out to the dredge, went aboard, and collected. We inspected everything, and we set up. We did a laser alignment measurement. The alignment was perfect. There was no problem with the alignment, and that was stationary, not static. And then we set up and ran it, doing this motion amplification study, And we also collected traditional vibration analyst data with a single channel handheld analyzer.
So we were also using the thermal camera.
And we also used an infrared thermal camera to check the temperature of the coupling and the components in the driveline. So what was happening was the coupling kept failing. This was a video concentrated on the skid, low on the unit. But you can see these arrows. So these are vector arrows, and they're showing the movement and the amplitude. So these are the pixel points we've been talking about. And you can actually put an arrow on that point, and then we could actually get FFT data from that as well, and waveform data.
Great. The scale of that arrow is roughly in, say, pixels or something, point around.
The scale of the arrow is,
So it does units of, I think it's in micrometers, but you can change it depending on the severity. Generally, what we'll do when we're trying to process this video is you can actually do orbits as well. So you can look at the max peak-to-peak displacement of the orbit itself, and that'll be your full displacement.
so you can get a plot that shows you the amplitude.
Yeah.
And we'll give you the,
And that arrow there is,
it's scaled to the other arrows. So in relation to the other arrows, they're all the same scale.
In this particular example, the orbit plot would look like an oval, and then peak to peak would be your max displacement from here to there.
So what
so on
these
and so forth.
arrows are showing here is that it's moving in phase and of similar amplitude. So you can see the gearbox here is pretty tall. And the skid, what we found out is that the skid wasn't rigid.
Yeah.
And the base below the skid wasn't rigid. So the whole thing, the base was in torsion, which was, of course, causing it to be out of alignment when running, which was tearing up the couplings.
That's actually one of probably the most common use case, I would say, for this technology is to really pick up on dynamic misalignment. So things can be aligned when it's not running, but then obviously when it is running, you've got all these dynamic forces. The gearbox is rocking back and forth due to the lack of the transverse rigidity, and that's actually throwing it out of alignment for each revolution and putting more stress and strain on that coupling
So
itself.
the coupling that was failing is behind the gearbox, going through the bulkhead, and that's going to the drive shaft that goes to the pump. So you can't see that, but you can see how much the gearbox is. This is the engine, flywheel, clutch, assembly, and that's where the most movement was. Okay, this shows you the external shafting, right? So you saw where it was going through the bulkhead, and this is where it came through, and you can see the rotation here.
So the particular point of interest on this one is the actual pipe right here.
So the pipe was also moving pretty significantly.
And if you notice, outside of all the others, these are actually moving 180 degrees out of phase. So it's doing this.
what was the fix on that?
They
Go ahead.
you want to go?
No, go ahead. Go ahead.
So they went back to the shipyard. Shipyard went back to their naval architects, and they reinforced the structure. I don't know that we were planning on going back, and they're like, wow, we got this. Once they saw what we did, they knew what they had to do. And I think there was the tank top structure wasn't stiff enough.
And we did recommend an ODS analysis to find out where they would need to specifically stiffen that.
But
That's
I
good.
think they knew right away, and and they were able to get it resolved. They don't want to pay more than they have to, right? All right.
So the next case study is actually on a commercial fishing vessel out in Alaska. So it's
This
a
Dutch
hybrid
Harbor?
electric. Right? Hybrid electric?
Yeah. Diesel electric plant.
Yeah.
With a shuttle Z drives.
So they had 5 diesel generator sets, and basically what was happening is when they got into those high seas, the really the rough sea conditions, the generators actually started to fail. Or did they fail or stall out?
No, they tore the couplings
Tore
off.
the coupling.
And
Okay.
they have 5 gen sets that power electric motors that drive the main propulsion through Z drives. And they were at a situation when they were in 30-foot seas, and I think 2 of the units had failed.
Something like that.
Yeah.
I think it was 4 and 5.
Yeah, they were down to 3 units, and they were, fighting, big seas in the Bering Strait, and it wasn't, it was pretty concerning.
So
And it was a relatively new boat.
yeah,
It was, again, it was,
Were they redound coupled or close coupled?
they were
close coupled skid mounted.
close couple skid mounted, yes.
So what's funny about this particular use case is this is actually the very first, I believe the very first case that we used this on.
Yeah.
So we actually rented the unit. We had heard about it, did some research. We rented a unit, and we went out and did this. Obviously, we got our guys trained up and bench tested everything out, so everything was working properly. But so we went out there and we did this.
Very bright FAU engineer.
It was. So as it kind of outlines here, we used the motion amplification to pinpoint what was causing these failures on the diesel gensets. Essentially what was happening is they had a mounting bracket that was not stiff enough in the transverse plane, again causing that twisting motion in the skid, which was
Causing the couplings
to fail.
Yeah.
So we identified that issue with the motion amplification. We actually designed and fabricated a new support bracket to provide that rigidity in the transverse plane. And then, we'll show the before and the after so you can really see it. But what's interesting of note here is that they had multiple contractors on this boat, and none of them were able to figure out this problem. So it was pretty cool that we were able to go on there with this new technology and figure it out and not only identify it, but provide them that solution. So if you look here, again, this was the first iteration. They've developed that software very significantly now. They've refined that filtering process, and it's much, much better now. This is kind of the earlier iteration, but you can see this bracket kind of shaking back and forth, right? So
It's not the best video of that bracket, but it was enough for us to figure it out.
I think I might actually have one
If you look,
zoomed in as well.
If you look here, you can see the relative motion between the unit and the base and the engine.
So where it's really more, I think most pronounced, to me at least, is right where that connection point is of the bracket and the skid. But yeah, it is tall support with just kind of a little bracket there for rigidity. It just wasn't sufficient.
And the other, you can see the fastener is actually coming loose. And don't ever use split washers because they split and then they lose their tension.
So it's a little tough to see now, but this is the bracket that we made. So I think it's actually got a stiffener down the middle as well. And we got rid of this and just bolted that directly to the block. And you can see
There was actually a very, very good machine shop in Dutch Harbor, Alaska. These guys they were good. They really were good.
But you can see that the skid's not moving anymore. It's quite stationary.
Yeah, you can see the filters moving.
Yeah.
You don't see that base moving anymore.
So one thing just of note, or of interest to note here, because of that filtration and the high-speed camera and the way it processes, it's very important that you get DC light on this. So if you noticed it was kind of getting dark and going bright, that's the line frequency on board from the AC power.
Yeah, so you need steady lighting.
Yeah. This one's a little bit better. It's a little more direct lighting.
Lighting is really key, and as in most video, you really need good lighting. We have some pretty powerful. We purchased some pretty powerful LED lights for this kind of work.
Yeah.
They don't, there's no cycling.
So again, if you ignore the screen moving, you can tell that the skid is no longer twisting the way it was before. And we've not heard from them since. So our motto is no news is good news, right?
So as this, another case study here is it was a brand new sport fish. What was unique about this vessel was the standard propulsion system was one brand of engines, and this owner wanted another brand of engine rather than what the standard offering was. So they were having some serious vibration problems. They were having alignment problems and vibration, did we align it? And then no.
Yeah, we did all the standard running gear
stuff,
things to address. We saw shaft rate. We saw I think we saw first order of engine rate.
Yeah.
We saw blade
I don't
pass.
think we did we do a pre-vibration survey?
I believe we did. I thought we did.
Okay. No, we didn't.
No?
No, we didn't. So we hadn't been on the boat until the captain, requested for us to do, standard running gear service, pull shafts, do alignment, that kind of thing. And then we did a sea trial. And like, something's wrong here. This ain't running right. So we investigated, and we used the motion amplification camera on this as well with some multi-channel data. And honestly, once you see this thing, you're like, well, you don't even need to do any of that to figure this out. You almost should have seen it without that. But we found that the support brackets, this was developed by one of their top mechanics at the builder with no engineering support. This is why you go to engineering school. So what he did was, instead of building a tower, he decided, I'm going to bring the bracket to the mount, not the mount to the bracket. So it's got this long support arm, and this thing was extremely weak. And not only was that weak, but the saddle that went down the stringer wasn't well secured to the hull, and that was also moving, which is making the problem even worse.
This is a very time delayed light flicker here, which is why it goes from light to dark.
This was moving, and this was moving.
Yeah, so
I mean, if you look at up there, you can really see it.
It's basically a very narrow support far below the center of gravity of the engine. So it's just doing this.
Yeah. A lot of mass up, unsupported. Not very stiff or rigid. So we took the rails off, the inboard rails. We didn't take the outboard rails off. They were okay. But we took the inboard, we took the mount off, we took the bracket off, we fabricated new saddles, we bedded them in and secured them to the structure, and then we fabricated these towers that were very rigid and stiff, and obviously you can see a huge difference in the amount of support there. And you can see now post-works. That's moving, but that's not.
The way it's supposed to be.
It's interesting, too, when you see the videos of the mounts. I mean, the way the mounts work is they take the higher frequencies generated by the engine, firing frequencies and rotational frequencies, and they reduce it through the mount. It decouples it and reduces it to the frequency of the mount. And the mount throws off the energy and heat. So it's important, like, some of the military ships, they'll actually put cooling fans on the mounts to keep them operating in top performance because they absorb quite a bit of heat. All right.
So,
Tony,
real quick, I just want to jump in. So you can see, instead of having a narrow support coming from the center of gravity down to the foundation, we've greatly increased the surface area of the foundation and brought the foundation up closer to the center of gravity, which helps to stabilize the machinery as it's running.
Yep. All right, that's it. We have more, but I'll have to save it for next time. All right, well, thank you, everybody. Appreciate your coming to see us. Tony, great job. Thank you.
Thanks for listening in. We hope you enjoyed our deep dive into this week's tips and tricks for equipment optimization. Want to learn more? Head over to AME's LinkedIn, Facebook, Instagram, or YouTube included in the show notes, along with details from this episode. That's all for now, folks. See you next time.